let's start with the place where we left yesterday. So basically what we have found is that for Schwarzschild black hole, R equal to Rs equal to 3m, 2m is the horizon, and R equal to Rp equal to 3m is the unstable circular null geodesic, or sometimes this is called photon sphere for obvious reason. This word is also used. Okay. Now, what we found is that if what we want to know is now that, and we also have understood how, if there is a black hole between me and the light source, how the light rays can behave depending on the impact parameter or the angular momentum of the light, which is coming from the light sources behind. Light can either come to me or get captured by the black hole, or there is a limiting case, which is R equal to 3m. That is very important, 3m. So what I would expect to see a radius, a black spot in the sky, a black circle in the sky, not R equal to 2m, but R equal to 3m. Okay. Again, let me emphasize that this is only for the light which is coming from outside behind the black hole. It is still possible that there are light rays between 2m to 3m, escape the 3m surface and come to me. But obviously, intensity wise, they will be very feeble. And therefore, what we mostly see is darkness between 2m and 3m, okay, compared to the brightness outside. Okay. So what are now we need to understand, after understanding, we need to ask this question that we want to know a little bit carefully study this idea that what is the angular diameter, okay, of the black hole I see in the sky. Okay. So this is something we are like to answer today. Angular diameter of the hole as we see in the sky. So we'll ask that I have a farther distance from the black hole. I'm looking at it. There are different light sources outside. How does the bending of light work? And if I move closer to the black hole or away from the black hole, how does it work? Okay. This is something we want to understand. Okay. So let us try that what happens and to understand this. Okay? So last time we have also seen that, let's draw the picture again. Here is the observer at, let's say, R equal to R0. This is what we call observer. This could be Earth, okay, or the Event Horizon Telescope looking at the black hole. Good. And here is the line. This is the R equal to 3m surface. Okay, please forgive my drawing. This is the R equal to 2m surface. Okay, so this is Rs, and therefore this is Rp, and there is some distance source from which the light is coming. Okay, so of course you know that if the light is from outside, impact parameter is higher than R equal to 3m, then this light will reach you. Okay, may reach you by bending or something. Okay, but if the impact parameter is less than R equal to 3m, it will not able to reach you. It will go to the horizon. It will ultimately fall into the horizon because there is no circular orbit inside this. There is only one circular orbit, and that also unstable. And there is a limiting case, which is this. Now there it could happen that it can go away several times and then come back to you, or there is other possibility to go away some back time and then fall into the black hole. Depending on how you are perturbing it, how the perturbations are at R equal to 3m, depending on two cases can happen. Either it shoots back, come to you as from infinity, or it just fall into the black hole. Good. So therefore we conclude there are three categories of light. Okay. So the derivation which I'm telling you is by Singe, which he derived is 1966. So, and I was initially thinking of doing it using Hamilton-Jacobi equation, but it turns out that that's sometimes is difficult. There is different alternative way of understanding the shape of the black hole in the sky. There is something which I should suggest. You look at the Chandrasekhar's book, The Black Holes, there is very interesting construction using what is called a celestial coordinates. Okay, the projection coordinate in the sky. That is a little bit rigorous. Okay, so maybe you want to look at that also. But then I discussed with one of my colleagues, Rajesh, and he told me that it may be better to use this approach. It is simpler. So that's why I'm using this. Okay, good. So there are three possible light rays. One is that light rays that goes to infinity. Okay, very good. Then there is another light ray possible, second, light rays captured by the black hole. Or rather, okay, I should, again, let me be careful, okay. I'm using the word black hole, but you know that it could happen, the central mass is not a black hole, but rather a very compact object, okay. And borderline case, there is a borderline case, and that borderline case is the when light can spiral at r equal to 3m. This is possible because this is a circular null geodesic, but a little bit of perturbation. It's an unstable orbit. Perturbation. And the ray either fall in or escape to infinity. Escape to infinity. This is what we mean by unstable orbit. Unstable circular orbit. Good. Okay. So now let us consider a very, very ideal situation. Okay. So when we say consider the situation when there are light sources everywhere in the sky, everywhere in space-time, everywhere. Okay, but not between the hole and the observer. So that means what I am saying is that the sky is filled with light sources. Okay, and there is a black hole. Okay, and I'm looking at it, but there is no source between my eye and the hole. Okay, this is a very, very ideal situation. But let's go ahead with this, okay, because we want to understand how it looks like. Okay, so in that case, for light ray 1, so let's say for light ray 1, that means the things which are coming from the light sources and reaching me, I should see brightness. I see brightness. Very good. For 2 light rays, case 2, I see darkness. Okay. And this darkness is what we define as the shadow of the black hole. Okay. And in fact, remember the boundary of the shadow is the unstable null orbit at rp equal to 3. Okay, so I should see a black circle in the sky if I am further away. Okay, what we want to do is what is the angular diameter of this shadow at R naught. So suppose the question I want to ask is that here is the shadow. So this is what I will see, but it will subtend an angular diameter here. This is R naught. So I want to know this angular diameter. What is this? Okay. And call this angular diameter to be alpha naught. Okay. This is something we want to calculate. I hope this is clear. Okay. In fact, one way to do that is if I define Cartesian distances here, delta y, sorry, not delta y. Give me a second. This is what I want to calculate. If I can define a distance here, delta x, and here a distance delta y, then the definition of shadow will be tan alpha equal to limit delta x goes to 0, delta y by delta x, but this is for the light ray. So this alpha naught for the light ray coming very close to r equal to 3m. Okay. See, I cannot say exactly the light ray which is exactly at r equal to 3m. I cannot say that it will come. Okay, because it may spiral back into the black hole. Okay, depending on the perturbation. But for physicist sense, I can think of that is the last ray which is coming to me. Okay, all other rays are going into the horizon, and the other, of course, is coming to me. Okay, give me a second. The other guys are also coming to me. Okay. So this alpha naught is the angle which we want to calculate. Okay, as a function of r naught. Okay. And you want to know what happens if I go very close to the black hole, go farther away black hole, how much portion of the sky I see this dark spot. Okay. So this is the interesting calculation which you want to do. By the way, this calculation is due to Singe. Okay. And okay, good. So let's start. So what we'll assume is that the plane of the paper, that means this plane of the iPad rather, okay, the plane in which I am writing is the equatorial plane. Equatorial plane. Theta equal to pi by 2. Okay. We can always work in the equatorial plane, but let's assume that everything is equal to theta equal to pi by 2. So we don't have to worry about change in theta. Okay. So we only have to worry about change in phi. So think of what I am doing. I am on a particular theta plane. Okay. So this is on a particular theta plane. That means, remember, this is the direction of theta. So I am looking at this plane. Okay. So whatever angles which are varying, so this is del r naught. And if I move along this direction, and this is delta y. Okay. So what I want to know is that if I move along these directions on this plane, this is the phi angle. Okay. So any angle in this plane, if I move, this is the phi angle. Okay. Good. So in that case, what is delta x? Delta x is not just like the proper distance. Proper distance, I will put, dt equal to 0, d phi equal to 0, d theta equal to 0, and then what is left it is nothing but my dx. So this is by rs by r equal to the power minus half dr. Okay, that's all my delta x is. What is delta y? We have to be a little careful. Remember that I told you that this is theta equal to pi by 2 plane. Okay. So any angle, if I move along this direction, this angle is a phi angle. Okay. So this is r naught is the distance. Okay. So how do I calculate that what is the delta y? So let's say this is delta y. Okay. If this distance is some r, okay, and then delta y will be r d phi. That's all. So delta phi will be r into d phi. Okay, right? So therefore tan alpha, I have not used this for, remember, I have not yet used. So one has to be a little careful. Where is r? Let me look at it. This is not really the r. What I'm thinking of r. So figure it out what exactly. So you should be able to understand this equations. Okay. If you do not understand, I will again talk about it. Okay. Remember, this is true for a particular light ray. This has nothing to do with the light ray coming at 3m. It is true for all light rays which are coming to you. Okay. I have to impose extra condition this condition, that this is for the light ray coming from very close to r equal to 3m. So I still cannot call alpha equal to alpha naught. I will call alpha equal to some alpha. Okay, that's all. Alpha equal to alpha naught when, okay, alpha equal to alpha naught when I will have light rays coming very, very close to the last ray. Okay, that will be my alpha naught. Good. So tan alpha is then equal to r defined by, okay, 1 minus rs by r half dr. Okay, and this is evaluated at r equal to r naught. Okay, and for any light ray which is coming towards me. Good. Good. Now remember, this is on a light ray, so I need to use the null geodesic equation sometimes. Okay, so let us go back and consider our radial geodesic equation. Radial equation. If you remember, we have derived radial equation. Let me write a null equation for the photon. If you remember, we have derived this equation that epsilon is equal to 0. That means E square by 2 equal to half r dot square. Okay, and then we have what did we have? Plus, I think plus or minus. Yeah, plus L square by 2r square, and then we have minus m, rather let me remind it, ml square by r cube. Okay, I put gc equal to 1 again. Okay, now what I do is that I can manipulate this equation. I can write r dot from here, which is dr d tau whole square, to be equal to e square. Let me bring out the c square again because it will be important. So there is c square here. Okay, it will be important to use the c square because you will see, or you may not actually, you can set 1 minus rs by r, and this is L square by r square. Again, our notation rs equal to 3. Sorry, rs equal to 2m, rp equal to 3. Okay, so this is the, sorry, r dot square. This is the r dot square we have. Good, remember this. Okay, again we have another equation. We also have phi dots square equal to L square by r to the power 4. This is just coming from the definition of the angular momentum. Okay, so we have r dot square, we have phi dot square. We can divide it and we can obtain the dr d phi equation. Okay, so we have dr d tau, we have dr d phi d tau. By dividing it, we can obtain dr d phi. And if you do that, you will see this equation is E square by c square L square r to the power 4 minus r square plus rs into r. Again, rs is 2m, the Schwarzschild radius. Okay, good. So therefore, what we can do is that this d phi by dr, this is for the light ray. Okay, so we can replace it by this equation. See, we want to write everything in terms of the conserved quantities r and r naught. Okay, that's all we want. Okay, so in that case, so now you can understand what is r then. Okay, so think of this is my r. Okay, so let's go ahead then. Okay, because it will be much easier if we can write things in terms of conserved quantities r and r naught. R is the position of the light ray. Okay, good. So therefore, using this, what you obtain, tan square alpha equal to, now you substitute this equation into the value of the tan square alpha, and you can immediately see this will be r naught square 1 minus rs by r naught, and then e square r naught whole to the power 4 c square L square, okay, minus r naught square plus rs into r naught. Okay, and you can simplify this further and you will be able to prove from sine tan square you can get to using the trigonometric identities, you can go to sine square alpha and you will have sine square alpha. Please do this simplification, this is easier to understand. C square L square r naught minus rs divided by e square r naught whole to the power. This is a very important equation. Okay, important. So this equation gives you the angular diameter alpha as a function of R naught and Rs. Okay. So where you are R naught, if you know that, okay, you know that what is the angular diameter of the alpha. Now the problem is, remember, there is a L square by E square. Okay. This will depend on what light ray you are using, the impact parameter of the light ray. Okay. But you want the angular diameter. So remember, for this is the R equal to 3m line, guy, radius. This is for any light ray. So this light ray should come from here. Okay. So then this is the angular diameter. But you don't want that angular diameter. You want for a very special light ray, which is this, the one which just in the R equal to 3m and then able to come to you. Because that angular diameter will decide the angular diameter of the black disk. Okay. So what you want? Alpha naught, not alpha. Alpha is the angular diameter of any light ray which is able to come to you with angular momentum L and conserved energy E. But you want the angular diameter of the particular light ray which is almost close to the R equal to 3m but could able to escape and come to you. Because if you know that angular diameter, that will be the angular diameter of the black spot which you want to ultimately calculate. Okay. So let me write it down. We want the critical angular diameter. Critical angular diameter. Alpha equal to alpha naught. Okay. Corresponds to the light ray. Sorry, not the light ray, the light ray. Light ray spiraling at R equal to 3m or 3 by 2 Rs. Okay. Okay. Now for that ray, remember we have derived last time that for that ray, if you remember last time we draw the effective potential and everything, okay, for the null ray, and we found that for that particular ray, the energy and angular momentum obeys a particular condition, that this is V effective, and this is, sorry, I should have drawn it wrong, should always be positive. Okay, and we've concluded that for this particular light ray, this energy E, for which there is a circular null geodesic, we have a condition C square L square by E square equal to 27 by 4 Rs square. Okay. Oops, sorry. This is an important condition. So for that particular light ray coming very close to the photon sphere, the L and E must be related in this way. So if we remember, we can go to the lecture 3. Okay, let's look at it. Where do we derived it? Okay, here it is derived it. Okay, so remember this is the limiting case. Okay, where this is the limiting case where E square is equal to L square by 54m square. Bring out the C, so this will be square by C square. Identify Rs equal to 2Rm, and then you will have our equation today. Okay. So this is the energy and the angular momentum relationship for this ray, the critical ray which we want. This is the one. Okay. Okay. Because this is the one which is parallel here. I mean, see, there is a little bit, caveat in this argument. I'm thinking about the ray which will coming very, very close. Okay, to the R equal to 3m. Okay, so this has to be true. Okay. Okay. So in that case, what we'll do is that we will substitute this equation to this equation. Okay, and that is the critical diameter. Then the critical diameter. Critical angular diameter. And what will be the answer? If you do that, you will get a very, very simple equation, alpha naught equal to 27 r square r naught minus rs. This is an important factor, 4 r naught cube. And this is a very, very important equation. And this equation is derived by a very famous relativist Swinge in 1966, I think. Okay? Okay, good. So what does this equation tells us? That if I look at the black hole, if there are light sources everywhere distributed behind the black hole looks to me a black spot. Okay. And the angular diameter subtend at that black spot is given by angle 2 alpha naught, where alpha naught equal to sine inverse square root of 27 rs square r naught minus rs by 4 r naught cube. Okay? Okay? Good. And this is a very, very important equation which you should remember. Note that very interestingly, if r naught is equal to r, you see what is happening. Okay. So basically if you move very close, so this is the r naught. Okay. So if you go close to the black hole in almost here, it seems the sine square theta almost goes to 0. Okay. Now figure it out. What does it mean? Okay. You should be able to figure it out. Okay. That sine theta is going to 0. Okay. When sine theta is going to 0, then alpha naught is equal to, and you understand what is going on. Okay. I'll leave it that to you. So what is the idea? That if I'm farther away from the r naught, I should see that I'm farther away from the black hole, large distances from the black hole. I should be able to see that black hole will have, looks like to me, a black spot, and the angular diameter of the black spot I can determine from this equation. Is this clear to everybody? So this is what we call the black hole shadow for spherically symmetric black hole. Black hole shadow for Schwarzschild. Okay. So I'll stop here and I will take if there is any question. So if there is any question, any doubt on this derivation, please let me know. There is only one question. It says, what do we see in case of other compact object in the second case? Okay, see, in the compact object, if it is less than or equal to 3m, let's call them a name, ultra compact object. That means who have their own photon sphere. Then mere observation of photon sphere do not distinguish them. Okay. So they will be, or for all practical purposes, behaves exactly like black holes as far as the photon sphere is concerned. So we cannot distinguish them by just looking at the photon sphere. We need other observation to distinguish a black hole and the spacetime. Okay. Is there any other question? I'll wait if there is any other question. This derivation well, I don't know what exactly you mean by gravitational lensing for r less than 3m. Note that if it goes beyond the r less than 3m, there is no circular orbit. Okay, that's all. You said the perturbation. Does the perturbation arise from interior black hole? I mean, yeah. So see, perturbations are always there. Okay, there will be perturbation. Okay, so it's like unstable equilibrium. So it's the maximum of the potential. Okay. If you are at the maximum of the potential, you can clearly see that this is unstable equilibrium. Give me a second, guys. Okay. Okay. So the perturbations are always there, right? I mean, there's always will be some perturbation in the EA case, I mean, real case. Okay. So these perturbations can, if you are at the maximum of the potential, two things can happen. You can go down in the one hill or you can go down in the other hill. If you go down in the one hill, you will fall into the horizon of the black hole. If you go down the other hill, you will shoot up to the infinity. That's what will happen. Can an accretion disk cause? Yeah, of course, anything, the matter there, anything will cause perturbation. Is there any other question? Why would we consider delta phi equal to no? But this is by definition. Delta x is in the direction of r, right? It's in the vertical direction, sorry, horizontal direction. So there is no delta phi there. You move along only in the direction of r, and then why you move along in the direction of changing phi. While calculating delta y, I have neglected delta r. While calculating delta x, I have neglected delta phi. That is definition. If you move along this direction, phi is not changing. If you move along this direction, r is not changing. Okay? Is it clear from the geometry? Okay, is there any other question? Regarding the derivation or the explanation, please let me know. I'll wait for a few seconds. Otherwise, I'll go to the next topic. Okay, if there is no more question, okay, please look at the delta x. When you move along this delta x, where is it? If you move along this delta x, okay, it's only r which is changing. Okay, the phi remains constant. Phi is this direction. Okay, if you move along this direction, r remains constant, only phi is changing. So delta x is related to delta r, and delta y is related to delta phi. Delta y is r delta phi. Okay, think of a circle. If you're on a circle, if you're moving along this direction, delta y, that will be, this is phi, will be r delta phi. Okay, if this is r. Okay, and this will be, if you move along delta r direction, this is delta x. Okay, for flat spacetime it is just delta r, but since this has a curvature, there is a Schwarzschild, there is a 1 minus 2m by r sitting there. Is this clear? Is this clear? If you can repeat, it will be very good if you can say. Yeah, good. Okay, great. Excellent. So let's go back to, so what we have understood, that for this discussion, we have understood the existence of the null geodesic orbit, unstable null orbit. We have understood that how the black hole will appear in the sky as a dark spot. Okay. No, origin is at the black hole, r equal to 0. Okay. That is the origin of the coordinate. Otherwise, r naught is the distance at which the particle is there. Okay, sorry, the observer is there. Oh, good. Okay, fine. Should I go ahead, everybody? I'll wait for a few seconds if there is further more questions. Okay, if it is not, let's go ahead. Good. So the idea now, what is that, well, we have understood that how everything goes well, excellent ideas. And we also understood, by the way, you should try that when you move closer to the black hole, what happens, okay? How the diameter of the shadow changes, okay? You should do some calculations, okay? With the sine theta, how much portion of the sky you see covered or something like that, okay? This will be interesting, okay? Good. Once we have learned all this thing, the next idea is that generalize everything for Kerr black hole, okay? The rotating black hole case. And why would we want to do that? Because the physical black holes are not spherically symmetric. And in fact, the Kerr black hole is the next best approximation of what is a physical black hole we see at the center of our galaxy or center of the, let's say, M87. Okay. Those are Kerr black hole. We believe they're rotating black hole. They have a significant rotation. Okay. And quite a bit rotating black hole. Okay. So therefore, we cannot approximate that situation as a spherically symmetric Schwarzschild black hole. It will be wrong. We expect that we should solve Einstein's equation for the rotating case when there's a rotation present and look for the solution and draw everything. Okay. And this is exactly the business of Kerr solution, which is developed by Roy Kerr in 60s. And this is one of the, extremely difficult and extremely important solution, okay? The Kerr solution. And okay, so it is not easy to solve Einstein's equation. Okay, because they are nonlinear equation and their partial differential equation coupled 10 partial differential equation. So what we want to do is to solve r mu nu equal to 0 outside the black hole, outside the rotating black hole or star. Okay. Okay, fine. This is what we want. And what is the equation we want to solve? R mu nu equal to 0. Okay, we cannot use the very simple idea that there is a SO3 symmetry. Now there are killing vectors like 3 SO3 killing vector. Of course, we are looking for a stationary solution. There is a time-like killing vector, which we can always assume. But beyond that, we cannot assume anything. Okay. It is clear this is not going to be a Szekeres solution. Why? Because there is a rotation, there is a rotational axis. Okay. So there is a preferred direction. Okay. With respect to the rotation. Okay. So therefore, those things are not SO3 symmetric anymore. Okay. So therefore, we cannot use the spherically symmetric answer. Okay. Not only that, because there is a rotation, we expect the space-time will endowed with now a angular momentum. See, earlier the space-time has only energy, the mass, okay, which is the energy of the space-time. Now we believe that since the space-time has rotation, we expect that there will be an angular momentum. So two parameters. First is mass, mass, which is there for Schwarzschild case also. But now we expect that there should be an angular momentum. Momentum G. Okay. So it is not easy to define this quantity J and M. For the particle is trivial. You can use the killing vector to define the angular momentum and mass energy of the particle. But for the space-time, defining its mass and angular momentum for the entire space-time is a little bit non-trivial. You require what is called the ADM formalism. You have to go to the asymptotic infinity, look at the Hamiltonian, and then look at the generators of various symmetries. But it is still possible to do a general formalism by which you can calculate mass and angular momentum of the space-time. Sometimes what we parameterize the solution by A, which is angular momentum per unit mass. Per unit mass. This is for the space-time, okay? This is nothing to do with the particle, okay? Unit mass. Okay? And solutions we expect that will be function of M and J or A, okay? This is something we expect, okay? Of course, we expect if J equal to 0, we expect J equal to A equal to 0, we should go back to Schwarzschild. Okay, this is what we expect. These are the expectations we have. Again, the question is that how do you write down this solution? You have to use some coordinates. See, in GR, coordinates does not have much of a meaning, but this is an oversold word, oversold sentence. Okay, actually, for practical calculation, you have to use coordinates. There is no way. Okay, and it is sometimes important to choose clever coordinates. Okay, well, all coordinates. Theory is diffeomorphism invariant, but for a particular solution, you will always express it using coordinates. Okay. So what we are going to do is that we will continue to use coordinates T, R, theta, phi. We can use other coordinates and write down Kerr metric. There is some special coordinate called Kerr-Schwarzschild coordinate. These things are a bit simpler, but we want to use this because in this coordinate system, the correspondence with the spherical symmetry will be obvious. Okay. Okay. So we will keep this coordinate system, but remember, one has to be very, very careful. Okay. One has to be a little careful that these are may not have as simple interpretation as for spherical symmetry. For example, R is also related to the coordinate distance in spherical symmetry, but that will be no longer true here. It is just a radial coordinate. Okay. And therefore, to distinguish it for spherical symmetric case, we give them a name, people who first tried this coordinate, called Boyer Lindquist for now BL coordinates. Just to distinguish them, that look, these are not as simple as spherical coordinates. Okay. Now we'll write down the famous Kerr metric. Okay. The derivation of the Kerr metric took several years. Okay. So the first solution of Einstein's equation for non-rotating case given by Schwarzschild, when I think 1915, just after the discovery of the theory. Okay. During the Second World War. Okay. Whereas the Kerr solution came in 60s. Okay. So you can imagine it took almost 45-50 years, okay, to get the Kerr solution. Okay. That is because these equations are enormously difficult. Okay. And also there are many, so you have to be careful about how to choose coordinates, how to solve this equation, what are the boundary conditions you will put. And this is after long effort by many people. Okay. Ultimately Kerr solved the situation and he gave us one of the most important solution for the astrophysical purposes, that given a rotating black hole or star, what is the space-time outside. Okay. So I am not defining rigorously, okay, what do I mean by rotation here. Okay. But you will see when we will discuss Kerr metric in more detail, things will be clear. Okay. That what do I mean by the space-time having a rotation. Okay. This is basically that there is, I'll come back to it. Let's go ahead. So let me write down the metric. The metric will look like -1 minus 2mr by rho square. I'll define what is rho immediately. Let me write it down first. 2ma r sine square theta rho square dt defined plus sigma by rho square sine square theta d phi square plus rho square by delta dr square plus rho square d theta square. Okay. And where, or let me again more simplified, I will write it minus rho square delta. I'll define what are deltas and what are sigmas. Okay, I have to write a lot of things. dt square plus sigma by rho square sine square theta d theta minus omega dt whole square plus rho square by delta dr square plus rho square d theta square. Okay. So let me refine what are those objects are. First of all, rho. Rho is related to r as r and theta, a square cos square theta. Immediately you see that this is not spherically symmetric because the metric coefficients has explicit dependence on theta. Okay. Delta is defined as r square minus 2mr plus a square. Sigma is defined as r square plus a square whole square minus a square delta sine square theta, and then omega is defined as minus gt phi by g phi. In fact, you can simplify further omega and you can see this can be written as omega equal to 2mar by sigma. Okay. So this is a huge metric. Okay. First and foremost, you should immediately check, put a equal to 0. Okay. First check. We'll come back to it. Check. A is equal to 0 or j equal to 0 because A is nothing but j into m. Okay. If you put a equal to 0, you will see that metric goes to Schwarzschild. This is something you should say, check. Schwarzschild. Okay. So if a equal to 0, the metric goes to Schwarzschild. You can check that each and every component of metric ultimately goes to that of the Schwarzschild. Okay. Good. Next, note that there is a cross term. Dt defined. That means the metric is not diagonal. Okay. Now this is sometimes causes extreme confusion. Okay. So look, I have a symmetric metric. Okay. G mu nu, small g mu nu is a symmetric matrix. I should be always able to diagonalize it. Okay. So why the hell is happening? Why there is a non-diagonal term? Okay. But this confusion arises from the fact that you should be always able to diagonalize it only locally. Globally, by using global orthogonal coordinates, you may not be always able to find a diagonal global orthogonal basis in which the metric is diagonal. Okay. Locally, of course, you can always have orthogonal basis locally, and you can always diagonalize the metric. Okay. It's a symmetric metric. Okay. It's always diagonalizable, but globally it is not. Okay. And this is why Kerr metric cannot be diagonalized everywhere in the ball linguistic coordinates. Okay. So this non-diagonal term is inhabitable. You cannot get rid of it. And it is this non-diagonal term which is, we'll see, defines when I define this is a rotating black hole. Okay. And we'll see the consequence of this non-diagonal term. Good. Interestingly, also note that this metric is independent of time. None of the metric component explicitly depends on time in this coordinate. Okay. So therefore, in this coordinate, the time invariance is explicit. And therefore, what we say, there is a time-like killing vector. Time-like killing vector. Exactly like Schwarzschild case, which we'll call, let's call it T alpha, just by notation. And in this coordinate system, Boyle linguistic coordinate system, this equal to star means in this coordinate system, Boyle linguistic coordinate system, this is 1, 0, 0, 0. Okay, good. But important fact, difference from the Schwarzschild, note that there is no T2 minus T symmetry. There is no such thing like T2 minus T symmetry. Okay. That is no longer true. Okay. Because of the presence of this del T del phi term. Okay. So that means this spacetime is not static. Okay. It is something to do with hypersurface orthogonality of the T vector, but for us, that's the definition. Okay. Next, note that there is an interesting symmetry. T2 minus T, phi 2 minus phi is a symmetry. Okay. So it makes sense that if you reverse the time and reverse the rotational sense also, nothing changes. Okay. That is still a symmetry. Okay. But spacetime is not static because T2 minus T is no longer a symmetry. So Kerr metric is an example of a stationary metric, but it is not a static metric. Schwarzschild spacetime is the example of both stationary and static metric. See, if it is static, it must be stationary. Other way around is not true. Stationaries may not be static. Kerr metric is an example which is stationary metric, but is not static metric. Okay, good. There is another killing vector, important. Azimuthal killing vector, azimuthal symmetry. So phi alpha is 0, 0, 0, 1, or the phi symmetry. Why? Look at the metric coefficient, nothing depends on phi. There's absolutely nothing in the metric which depends on phi. So therefore, in this coordinate also, the phi symmetry is obvious. Okay. If you make a rotation in phi, move along the direction of phi, nothing changes. This is exactly what we call the axis symmetry. So this is an example, illustration of axis symmetry. Okay, good. Excellent. Now, we also need the inverse metric sometimes. So you can go ahead and calculate the inverse metric, which I'm not going to do. See, I mean, none of you I expect to do this calculation by hand. Okay. But maybe once you should try it with hand. Otherwise, it's okay to use any of the softwares like Mathematica, GR Tensor, or any other Tensor packages. Okay. Will immediately give you the inverse metric. There's one line. You don't have to do anything. Okay. Good. Now, just like the Schwarzschild case, let me anyway write down the inverse metric. I have this metric in front of me, which is minus sigma by rho squared delta GT phi equal to minus 2 MAR by rho square delta, GRR equal to delta by rho square, G phi phi equal to delta minus a square sine square theta divided by rho square delta sine square theta, and G theta theta up equal to 1 by rho square. Immediately you see that there are two possible sources of singularity. Okay, what are the possible singularities? Just like in Schwarzschild metric, r equal to 2m and r equal to 0 were two possible singularities. Here you can clearly see possible singularities. Singularities can occur when delta equal to 0, that is when r square minus 2mr plus a square equal to 0. Note that if a equal to 0, this is exactly r equal to 2m. Okay. Another possibility is that when rho equal to 0, okay, which is r square, what was the rho, remember? R square plus a square cos square theta equal to 0. Again, note that if I put a equal to 0, this is r equal to 0. Okay. So these are the possible sources of singularities. Okay. Now some of the singularities will be, just the coordinate singularity, or some of the singularities could be just a real singularity. Just like in Schwarzschild case, r equal to 0 turns out to be coordinate singularity, and r equal to 2m, r equal to 0 turns out to be the true singularity, and r equal to 2m turns out to be the coordinate singularity. How do you do that? Exactly in Schwarzschild case, we'll write down a scalar invariant. The easiest, the first non-trivial scalar invariant is the Cressman scalar, because RAB is 0, R is 0. So the first non-trivial scalar invariant n is Cressman scalar. If you write down that part, R alpha beta gamma delta, R alpha beta gamma delta equal to 48 m square r square minus a square cos square theta rho to the power 4 minus 16 a square r square cos square theta by rho to the power 12. Okay, you can clearly see at delta equal to 0, absolutely nothing will happen. It will be perfectly well defined, just like the Schwarzschild case at r equal to 2m. Okay, then there is absolutely no point. Okay, so in that case, delta equal to 0, I conclude is a coordinate singularity. Coordinate singularity. And but rho equal to 0 is a serious condition. Okay, the scalar invariant itself diverges. That means if it diverges in one coordinate, since it's scalar invariant, it will diverge in all coordinates. So by choosing a clever coordinate, you will never get rid of this divergence. Okay, so therefore rho equal to 0 is a real singularity. It's a physical singularity of the matrix. But it's a bit different from the Kerr, what the Schwarzschild case. See, Schwarzschild, look, r equal to 0 is a point, but here you have r theta is a kind of a ring. You will see, I mean, if you study later, I don't know whether I'll be able to cover that this singularity is actually a ring singularity. Okay, and it's time-like. You should be able to avoid it. Okay, anyway, that's not important for our case. We will never going to never go to the close to the singularity. Those are dangerous place. Okay. It is always better to be avoid the singularity, so we'll be outside. Okay. Now let us understand the geometry of Kerr. So this metric is huge. Okay, this is a too complicated metric. Okay, this is the metric. But let's understand very simply what is the geometry of this metric. Okay, little bit careful. So how did we understand the geometry for Schwarzschild case? Okay, what Schwarzschild case we did? Remember the Schwarzschild metric is ds square equal to minus 1 minus 2m by r. Let's see Schwarzschild. This is Schwarzschild. Dt square plus dr square into 1 minus 2m by r plus r square d omega square. Okay, good. Now for Schwarzschild metric, let us take the condition that t equal to constant, r equal to constant surfaces. So t equal to constant, r equal to constant. T equal to constant means I'm looking at constant time hypersurfaces. These are volumes. And then I'm looking at surfaces at constant R. So these are compact surfaces. Okay. And you can clearly see the metric on this. These are two-dimensional surface. So therefore, metric will be two-dimensional, equal to R square d theta square plus sine square theta d phi square. And it's clear this is the metric on a two-sphere. Okay. So that means T equal to constant, R equal to constant surfaces are sphere. These are geometric sphere. Geometric sphere. And this clearly shows that R is a radial coordinate. Another equal way is to see, calculate the area of this sphere. Area of these spheres. How do I calculate the area of the sphere? Is integral root sigma d2x, where root sigma is the determinant of two metric. Two metric on the sphere. Okay. And if you calculate this determinant, you can clearly see this determinant is square root of r square into r square sine square theta. That is r to the power 4 sine square theta d theta d phi. Okay, fine. And if you, this is for r equal to constant, so 4r goes out, r square, and we have theta equal to 0 to pi, phi equal to 0 to 2 pi, sine theta d theta d phi. Okay. And if you calculate this, this just gives you 4 pi r square, which is expected, the area of a sphere. So we did the class 10 calculation of area of a sphere. Okay. So this clearly shows that r, which is a radial coordinate, is also the distance, coordinate distance between the points at the center to some point at coordinate r. Okay. Good. Schwarzschild geometry has a spherical symmetry. Okay. So we understand the geometry. Geometry is that at every constant r surface, my coordinates are chosen in such a way that t equal to constant, r equal to constant surfaces are sphere of radius r. So I can think of packing this room with a stack of spheres, concentric spheres, and then moving along the direction of time. And that's my space-time is. So close your eyes, think of the stack of spheres, okay? Each at different values of r, theta and phi can vary over the sphere, and then move with this room in the direction of time. Anyway, you are moving in the direction of time, okay? That's what your space-time is. The coordinates and the foliation of the space-time is. Okay. Now let's understand what is this in case of Kerr space-time. Okay. So let us understand the same for t equal to constant, r equal to constant surfaces in case of Kerr. Okay, what happened for Kerr metric? Okay, so if you put t equal to constant, r equal to constant, you will see equal to. By the way, look, this is at a level which I'm not going to do all the calculations. Nobody will do. Okay, I mean you have to go back and do this calculation. Otherwise, you will never be able to understand. Okay, so I request you, take any of the standard books and derive, okay, and then it will be clear to you what is going on. Sine square theta, d, sorry, my mistake, d phi square, this fine, plus rho square, d theta square. Where sigma, we have defined sigma. Where did we define sigma? Here, this is sigma. So let's write it down. Equal to r square plus a square whole square minus r square delta sine square theta. I hope I've written all the factors correctly. A square delta sine square theta. Sorry, not r square. Sorry, my mistake. A square. Good. And what is rho? Rho equal to r square plus a square cos square theta. It is immediately clear this does not look like a two sphere. Okay, geometric two sphere to nail it. It's a compact two surface. Topologically, it's S2, but geometrically, it can be anything complicated. Okay, it's a complicated object. Okay, so let's understand the area. Okay, so how we'll calculate the area? Area, the definition remains same: square root of sigma d2x, and therefore this is equal to integral theta equal to 0 to pi integral phi equal to 0 to 2 pi. These are the ranges of these coordinates, obvious, the spherical coordinates, so they have usual ranges. And then if you calculate it, the answer will be sigma sine square theta. If you take square root, so determinant is equal to sigma sine square theta. So if you take a square root, you will have square root of sigma, which is r square plus a square whole square minus a square delta sine square theta. Then you will have sine theta d theta d phi. Obviously, this is a complicated integration. Okay, we are not in an integration class. So let's evaluate it as a position where let's at least evaluate a position where the integration is simpler. Okay, so evaluate it. Let's evaluate it. Evaluate it at delta equal to 0. Okay, and remember what was delta? Delta equal to r square plus a square minus 2m equal to 0. So I choose a position which is a solution of this equation. This is a very special position. We'll come back to it. Note that if a equal to 0, this is r equal to 2m. Okay, so it's a very, very special position. We'll come back to it, but for time being, this is a position. Okay, and then suppose this gives you r equal to r plus rh. Just notation. Okay, for the time being, I'm not saying anything like horizon. Just a notation. This is a solution of that equation. In that case, area at r equal to rh, you can immediately calculate this integral, and the answer will be 4 pi rh square plus s square. Note that r equal to rh surface, it's clear this is not a sphere. Otherwise, the area will be 4 pi r square. Okay. Okay. This is r equal to constant surfaces are not spheres. Okay. Actual area is quite complicated. Okay. R equal. So it means this simplified notion that r equal to constant, t equal to constant surfaces are compact to spheres, geometric spheres, is totally gone in Kerr. Kerr, they are quite complicated. They are compact object, compact geometric, topological sphere, S2. Topologically, they are S2. Okay, but geometrically, they can be anything. Okay, they can be very, could be an ellipsoid. Okay. Okay. So therefore, it's a complicated place. Okay. So this is to emphasize that r is just a radial coordinate. Beyond that, it does not have much of a meaning. Next. We also want to understand certain important points. So then let's understand in what sense this is a rotating black spacetime. So of course, I'm not going to calculate the rotational angular momentum of the spacetime, which requires ADM formalism, or the mass of the spacetime. We also require ADM integrals. Those are beyond the scope of this particular lecture. But let's look at a very, very simple illustration, that consequence of the existence of this d phi dt term. Okay, and these are called zero angular momentum observer. Angular momentum observers, and sometimes we call ZAMO. Okay. So to understand these ZAMOs, let us consider we have an observer. Need not be geodesic observer. So here is an observer. Okay. In fact, it will not be a geodesic observer. And for that observer, the 4 velocity u alpha is defined as dx alpha by d tau. Okay, that's the 4 velocity of this observer. Obvious. Good. Now, how do I define the angular momentum of this observer? Very simple. Take the 4 velocity, dot with the phi killing vector. Conventionally, put a minus sign, and this is your angular momentum. Angular momentum. Nobody will, oppose you. Okay. And how do you define energy? Instead of phi alpha, use T alpha. This quantity is conserved if and only if the particle is moving on a geodesy. Okay. Okay. Now let us look for observers with L equal to 0, where angular momentum remains 0. So angular momentum is conserved. Note, it need not be a geodesic observer because there is also another quantity, energy. It could happen for this observer, the energy is not conserved. So therefore, it could be an accelerated observer. Only angular momentum is conserved, always zero. Okay. Okay. So energy is not conserved. Okay. In fact, it turns out ZAMOs in Kerr spacetime, they are not geodesic observer. They are accelerated observer. Okay. So let's say what is the condition for L to be 0? Now in Boyle linguistic coordinate, we have defined this object to be 0, 0, 0, 1, the phi killing vector. Okay. So therefore angular momentum is just minus u phi into phi phi rather. Okay, phi phi. Okay, that's the only term which will survive, which is nothing but minus u phi. So L equal to 0 implies u phi equal to 0. Now that doesn't mean angular velocity is 0. Okay, this is the covariant component. So therefore, what you now need is that consider u capital phi. Okay. Note that if we have a diagonal metric, that means the metric for which there is no dphi dt term. Dphi dt term globally, which is exactly like, for example, the Schwarzschild metric is. Okay, in that case, u phi is nothing but g phi phi u phi. That's all. It's a diagonal metric, no mixing of anything. Okay, no g t phi term. This will be the case, or g r phi terms or anything. This will be the case. Okay, so therefore it will be 0 if u phi equal to 0. Okay. Now, what is u phi? Capital U phi is d phi d tau. Okay. Because it's a proper time, I can think of this as so equal to 0. Good. So it means the angular velocity is also 0. So if a space-time, including flat space-time, it is obvious if object has no angular momentum, it will not have an angular velocity. So 0 angular momentum implies 0 angular velocity. This is what we are used to. Okay, we are used to this. Okay, now consider the Kerr case. Consider Kerr case. And I told you in Kerr case there is a g t phi which is not equal to 0. There is a d phi dt term. Then what will happen? Let's calculate. So L equal to 0 will still mean u down phi equal to 0. But now u phi equal to g phi phi ut u phi plus g phi t ut. Okay. And one could have non-trivial angular velocity, need not be 0. Not be 0, as ut is not equal to 0. Okay. So therefore, what we have is that u phi is g t phi ut not equal to 0. Okay. So therefore, we can have a situation L equal to 0, but u alpha equal to u phi equal to d phi d tau not equal to 0. Okay. So you can have non-trivial observer, okay, which has angular momentum to 0, but still has angular velocity. It's very strange. So they are rotating, they have angular velocity, but they don't have angular momentum. Okay. Not only that, very strange, look at the angular velocity omega. What is the angular velocity omega? They are defined with respect to the coordinate time, that d phi dt is the angular velocity. So therefore, this is nothing but d phi d tau by dt d tau. And in terms of the components of the velocity, for velocity, this is nothing but u phi into ut. Remember that u alpha equal to dx alpha by d tau. So u phi equal to dx phi, which is just phi, d phi by d tau. Ut dx0 is dt by d tau. Okay. So remember this, very, very insignificant sometimes, but important nevertheless. But tau is a proper time. This is a time-like observer. I'm thinking of this as a proper time. Good. Okay. So therefore, what we have very carefully, what should be the omega for this ZAMO, zero angular momentum observer? For ZAMO, we just found u phi equal to 0. That has to happen. That means gt phi ut plus g phi phi u phi equal to 0. So therefore, this implies omega, which is equal to u phi by ut, which is equal to minus g phi t by g phi phi. Okay. Okay. So this value of omega, if omega you choose to be this value, if you have an observer which has an angular velocity this will ensure, this ensures u phi equal to 0 and therefore L equal to 0. So observers with this particular angular velocity, you can show they have zero angular momentum. Okay. Now note that this is something we have actually calculated from the Kerr matrix. So you took the g phi t, take the g phi t for the Kerr, g phi phi for the Kerr, and you will be able to prove that this omega is nothing but 2mar by sigma. Sorry, why it's not 5? This is thinking about sigma and drawing 5. Okay. So observers with this angular velocity, their angular momentum is 0, but they can have this angular velocity. Okay. Now this is very strange. Note that the omega is exactly same sign as the A. So what is happening is that these observers are co-rotating. They're rotating in the direction of the A. So this is a characteristics of a rotating spacetime. In a rotating spacetime, in a non-rotating spacetime, in non-angular angular momentum equal to 0 angular momentum equal to 0 observer does not have any angular velocity. Because of the presence of rotation, okay, the angular momentum equal to 0 observer can have angular velocity, and they are actually co-rotating with the black hole because omega is in the same direction of the J. M into A is J. Okay, so this is, you can think of this is nothing but 2jr by sigma. Sigma is always positive. Ensure that as long as your sigma is always positive. So therefore, what you see is that this zero angular momentum observer are like rotating with the black hole. This is the characteristic meaning of rotation, that it gives angular velocity to observers which does not have angular momentum. Okay, and it is an important thing. So for example, if you have a gyroscope, if you can ensure the gyroscope has zero angular momentum, you should see non-zero angular velocity. Okay, and that angular velocity will be measurement of the angular velocity or angular momentum of the space time. Okay, and that is why whenever there is a d phi dt term, we conclude that there exists a rotation in the space time. Okay, let me again say that this observer is not a geodesic observer. This observer is a what is called the non-zero acceleration, because the energy need not be conserved. Angular momentum is always 0, that is conserved, but energy is not conserved. Okay, so it has a non-zero acceleration. Okay, good. So this is the way we understand the consequence of the d phi dt term. By the way, this is what is called the lens steering effect, that a gyroscope with non-zero angular momentum, sorry, zero angular momentum having zero angular velocity. Okay, and this has been observed. Okay, in fact, I mean, even you can detect, see, the Earth is also rotating. Okay, so outside the space-time is almost similar to Kerr. Okay, the rotation can also be the lens steering effect corresponding to Earth can be just actually measured, has been measured. There is something called gravity probe experiment in the satellite. People could able to do it, and then it matches with the general relativistic prediction very well. Okay, anyway, those are important issues. So again, let me emphasize, there are two killing vectors for now. Okay, at least two killing vectors we found, killing vectors, which we can identify. We can identify now. identify easily. And these are T alpha, which says the space-time is stationary, and phi alpha, which says the space-time is axisymmetric. Okay, good. So apart from the JAMOs, the usual observer will be, another observer will be static observer. Who is a static observer? So I say, so look at me. Say, ignore the gravity. Suppose I am in the flat space-time. I am a static observer. Why? For me, neither r is changing, nor theta is changing, nor phi is changing. No, only the time is changing. Okay, I'm going near to the end of this course. Okay, end of this class. Okay, so therefore, my u alpha static observer is something like u alpha will be proportional to 1, 0, 0, 0. That will be proportional to T alpha. It does not be same as T alpha, because T alpha, U alpha has to be normalized to -1. So let's say it has this value, okay? Some proportionality to T alpha. So it's only moving in the direction of time. The guy which is not falling into the black hole is not static, okay? Static observer, because that observer is decreasing R, okay? If you're rotating, not static, because the phi is changing, okay? Observer is like sitting outside. So there is a black hole, I'm sitting. Of course, static observer cannot be geodesic observer, because to sit at same point, I have to apply force against the gravity. So therefore, I must carry a rocket, which will nullify the effect of the gravity. So therefore, I must be accelerating. Okay. So the static observer is defined for Kerr case observer. The definition is for velocity is proportional to gamma into T alpha. This is the static observer. Okay. Of course, with the caveat u alpha equal to -1. The observer means it has to be time-like. Okay. Note that I'm using minus plus 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 signature. So time-like vector is normalized to u alpha -1 in my notation. Okay. Another case we will look at tomorrow carefully, stationary observer. Stationary observer is the guy. Of course, it has a non-zero ut, but it can also have rotation. Okay. It need not have a radial. It does not have a radial direction, so it doesn't fall. It's stayed. Think of a planet revolving around the sun. That's a good example of a stationary guy. That guy, of course, in time it is revolving, but it also has a phi dot. Okay, so it's a phi component. I can ignore the theta component, and does not have any radial component. Okay, it doesn't fall into the black star or the whole central object. Okay, so for stationary observer, the definition is gamma. There is a T alpha, and then I call this omega phi alpha. Okay. So that means it has something like that: gamma 0, omega gamma 0. Okay, that is the definition. Okay. What is the meaning of this omega? Gamma is just the proportionality constant. This has nothing to do with the gamma of the special relativity. This is just gamma and function. What is the meaning of omega then? Note that omega, you can clearly see from here, is u phi by ut. And that is nothing but d phi d tau by d phi, sorry, my mistake, dt d phi d tau. And that is nothing but d phi dt. So therefore, the coordinate angular velocity. Angular velocity. So a stationary observer has a phi direction component, and omega is we identify as the angular velocity. Okay. Again, we must have u alpha to be -1. Note that I'm using same u alpha for both the observer, but they are different u alphas. Okay, you know what I mean. So next class, we'll identify and understand the consequence of this u alphas, and then we will discuss what do I mean, what is the shape of the shadow. Of course, we'll not derive everything qualitatively for Kerr black hole. And then we'll try to understand, given the shadow, what information I can obtain about the central object. Okay. For example, does the shadow observation tells me whether the central object is a black hole or some ultra compact object. Okay. So I'll stop here today and I'll look for the questions. Let's see. Okay. Okay, how can we associate properties like mass and angular momentum to spacetime? Look, this requires ADM formalism. So what you need is the write down the Lagrangian of the gravitational field, okay, calculate the Hamiltonian and find the value of the Hamiltonian for different asymmetries. So basically you have to figure it out, the no other quantities, okay, no other conserved quantities, okay, for the spacetime Hamiltonian. This is what is called the ADM formalism. Okay, a good reference for the ADM formalism is the book by Relativist Toolkit by Eric Poisson. It has a beautiful construction of the ADM quantities. You can look at it, how to calculate what is the interpretation of M and J in the angular momentum and the mass and angular momentum for the car. Do we know all the solutions? Oh, no way. Einstein. So, well, you have to be a little careful. So there are certain uniqueness theorems. For example, if you're looking for vacuum solutions of general relativity, stationary vacuum solution, which are asymptotically flat, okay, it turns out the only solution is Kerr. Sorry, stationary vacuum black hole solution outside the black hole, and which is asymptotically flat. It turns out the only solution is Kerr. So there are certain uniqueness, very powerful uniqueness to these solutions. Therefore, they are very interesting in physically. But in the presence of matter, we don't know much about all possible solutions. And without the symmetry, it's impossible. It's very difficult. Okay. Except you have to use numerical relativity in certain cases. Why does T2 minus? That's a definition of spacetime being static. This is related to the fact that T alpha, whether this is orthogonal to the hypersurface orthogonal everywhere. Okay. So I again ask you to look at toolkit, the relativist toolkit, which will tell you why this is related. But otherwise, take it as a definition of staticity. It's simply related to the fact whether T alpha is hypersurface orthogonal everywhere. It turns out it is not possible to do that in curved wave, as long as there is a divided term. Can we have a space-time where the metric component? Yes, you can. Why not? Because it's very simple. No, you have to be a little careful. You are absolutely right, but remember T2 minus T symmetry only makes sense when the spacetime is already static. Already stationary. If you have a stationary spacetime and then T2 minus T symmetry, you call it static. If you have something goes as T square, it is not even a stationary spacetime. Even if it has T2 minus T symmetry, I won't call it static. So first, I will have a stationary spacetime. If that stationary spacetime has T2 minus T symmetry, I call it static. Okay. So what you said, it have a symmetry, but it's not even a stationary spacetime. So I'll not call it a static. Is it clear? If it is not clear, also comment. Huh? If it is clear, also please comment. Then I know that I don't have to tackle that question. So if it is clear to you, the answer, please write that it is clear. The past could have evolved in certain way from minus infinity to 0, and then 0 to infinity in a symmetric way, right? Well, I don't know what does this statement means. Probably the key lie in the point there is no absolute origin. Therefore, well, I don't know. I mean, these words is difficult for me to understand. So the only thing I know is that if the space-time has a time-like killing vector, that means nothing depends on the time translation. Okay, we call the space-time to be stationary. This is a coordinate independent way of saying nothing depends on time. Okay, that's all. Now on that stationary space-time, if there's a no cross term globally, then we call it static. Okay. That is related to fact that this T alpha, the time-like killing vector, is it hypersurface orthogonal everywhere. Okay. What is the event horizon is always spherical surface? No, event horizon is not always a spherical surface. Kerr's event horizon is not a spherical surface. It's a compact surface with topology S2. Okay, that is important. Its topology is always S2. Okay, it need not be a, it need not be a football. It could be a, surface of a, what should I say, ellipsoid. Okay, topology is S2. It need not be sphere. And the question is a very important question because there is a theorem, something called Hawking topology censorship topology theorem, which says that the cross section of the event horizon, if you go to t equal to constant and event horizon, of course, r equal to constant, the cross section t equal to constant section of the event horizon, little bit careful, t is not the good time coordinate on the event horizon, but whatever coordinate you use, the cross sections of the event horizons are always compact to sphere as long as you are relating with certain energy conditions and certain other technical conditions hold true. Now, this actually is a quite interesting statement because this shows that in general relativity, the topology is somehow related with the Einstein's equation. In fact, there are very, very powerful theorems, something called topology censorship theorem, that tells you that as long as there is a black hole outside, the topology is completely trivial. Okay, you cannot have like multi-genus solution. Okay, outside. Okay, otherwise you will violate some kind of energy conditions. Okay, these are called topology censorship theorem for asymptotically flat spacetime, and they are important theorems. So, what would be the physical consequence of angular velocity? Okay, you will Earth near Earth been significantly compared to physical consequence of the angular velocity of space-time. Let's think about near Earth. So it's in Earth, it is extremely small, this effect, because the rotational energy contribution to the gravitational field for Earth is extremely small compared to its mass. Okay. Okay. This looks, if you put G and C, everything, you will see that there will be a C square coming, and that is killing all the ratios. So therefore, the lens-swing effect is very difficult to detect, but it has been detected. That's the whole point. This is something what is called the dragging of inertial frame. What I discussed, that there is a zero angular momentum observer which is being dragged with angular velocity. Okay. What is a stationary spacetime? By definition, a stationary spacetime is a spacetime which has a time-like Killing vector. That's the definition. What it means is that there's a time translation invariance. If you now use the adopted coordinate system related to the flow of the Killing vector, then you can make it independent to the time coordinate t. That's all. Okay. So a stationary spacetime is a spacetime which does not depend on time. There's a colloquial way of saying, technical way of saying will be it has a time-like Killing vector. In the Schwarzschild black hole shadow, non-zero in alpha. When taken as one. Okay, you figure it out. It means, see, we have, so it could well happen that, okay, that's a good question, but I ask you to plot the amount of sky you will see for which, if you had R equal to Rs, what happened? Okay, even if you are R equal to, let's say, between 2m and Rm, okay. If there is more, if it is more than what would be the, oh no, of course you will see lot of you will see lot of rotation. Okay, I mean, you will see lot of angular velocity in your gyroscope. That will be the physical consequence. Otherwise, I don't think there will be any harm. Okay, that's all. Is there any other question? Any other question? I have a question about null surface. A very null surface, the light cone is a hypersurface on which photon can travel and exist. Does the horizon also the horizon also have this property photon? Oh yes, in a sense, null surface. So flat space null surface is flat space null surface. You can think of the sphere, light sphere, going in a outward direction. So every cross section of that null surface, it is a two sphere, and the two sphere is radius is increasing. So the area of the two sphere is increasing. Close your eyes. Think of the two sphere. Light is emerging from a point, and the area is increasing. So there is an expansion of the area. Such null surfaces are called expanding null surface. You're absolutely right. Horizon is a null surface. But what is strange is that horizon is at least the Schwarzschild horizon or the Kerr horizon is a non-expanding null surface. So it means the photons, the R does not change. Okay. R does not change. Okay. Okay. Is this clear? So these are called, so the photon always remains at R equal to constant. Okay. So therefore R equal to constant surface is equal to the null surface itself. So these are called non-expanding null horizon. Okay. Yes. How do the force velocity you said is proportional to T alpha? Okay, so let's see the force velocity I'm looking for the force velocity of a static observer. Okay, the static observer means it has forward velocity only, the component of the forward velocity is 0 in r direction, so r is not changing, 0 in phi direction, phi is not changing, and 0 is theta direction, theta is not changing. So the only component it can have is in the t direction. So therefore it is something proportional to the 1 0 0 0, and the something is actually the component in the t direction. Is it clear? Is it clear, the forward velocity? Is part clear, the forward velocity part? Okay. Now the right, can I direct again what I need to do? Understand? Is it direct? Oh, I'll come back to this question in the next class, because this is something to do with how the shadow will look like when I move. I'll do it for the Kerr black hole and you will see. Okay. Good. Is there any other question? This is the reference is Relativist Toolkit by Eric Poisson. Okay. Or you can look at the review by Townsend. Okay. Black hole review by Townsend. These are good references. Or you can look at Padmanabhan's book, Paddy's book on general relativity, Introduction to General. And I don't remember the full title. T. Padmanabhan, General Relativity. Will get this book. That is a very extensive derivation of all the details of the ADM formalism. Okay.